This series of videos or lectures will be useful to the study of elasticity, fluid mechanics, continuum mechanics, I would say in general thermal science. Now, consider a square matrix P and a square matrix Q, then the trace of the product PQ is equal to the trace of QP. Now, let's show this using a very simple example. So let's P a square made 2 by 2 and Q 2 by 2. And this PQ, this is QP. So the trace is the sum of the diagonal, the main diagonal elements, okay? Now, let's do here. The first row, first column, look, first row, first column. So this will be P11, this Q11 plus, now P12 times Q21. Now, we forget about this term over here and that term over here. So this is the term second row and first column, and this will be first row and second column. Let's work only with the main diagonal. Now, here is the second row and second column. So it will be here P21 times Q12 plus P22 and Q22. You see, P22 times Q22. Now, let's do the same procedure using Q times P. So first row, first column. So Q11, P11 plus first row, first column, Q12, Q12. Now times P21. Now here you'll be the second row, second column. Second row, second column. So Q21, P12, Q21, P12 plus Q22, P22. You see, second row, second column. Q21, P12 plus Q22, P22. Now you see, if you add this first row, first column plus second row, second column, you see, this is the trace of PQ. Now, here, if you add the main diagonal, see, this is the trace of QP. Now let's add. You see, P11, Q1 is here. Now P12, Q21. Look, it's here. So this term over here, see, is right here. I'm adding. Now, in this case, P21, Q12 is right here. See, this and this. And the last one, P22, Q22 is right here. So the trace is important. Trace of PQ is equal to trace of QP. You could generalize using n by n. Okay, just to show this simple example. This will be very important. What we are going to do next, when we will be studying, for instance, stress tensor, you see that these properties will be very important to this study. Now, this will be later. Now, properties of similar matrix. First one, okay, what is a similar matrix? A similar to B, so in this case A is equal P, B, P minus 1. Don't forget, P is the transition matrix. Transition matrix. P minus 1 is the inverse. So when we work with the orthonormal system, P minus 1 will be a P transpose. But this is a particular case. This is general. Now, let's see. Okay, don't forget videos, 10 videos about Jordan form. Don't forget this, okay? All these details will be there, like similar matrix and so on. So let's see the first property of similar matrix. So A is equal B, let's put P, B, P minus 1. The first property is trace of A is equal trace of B. Let's show that. A and B must be similar matrix, okay? Must be similar matrix. Now, look, let's substitute here. Trace of what is A? A is P, B, P minus 1 is equal. See, this A, PB. Remember, AP is equal PB. We got this, okay, before, on the last lecture, last video. Now, let's do as follows. Let's call this PB, let's call this Q. You see, PQ, do you remember? Now, PQ, this is equal trace of QP. You see, trace of PQ is equal trace of QP. Now, I'll substitute again Q over here. So this is equal trace of, what is Q? Is B, P minus 1. That's Q times P. See? This is Q. Q over here. So, P minus 1 times P, this is identity matrix. The identity matrix times B, this is equal trace of B. So, trace of A, this is trace, here is trace of A, is equal trace of B. I use the property, you see, that I can make a permutation between P and Q. Determinant of A is equal determinant of B. You see? What is A? A is P, B, P minus 1. This is equal, I put here determinant of A is equal. Now, determinant of the tree matrix, I can put determinant of P, determinant of B, and determinant of P minus 1. So those are numbers. Okay, determinant is a number. Matrix is an operator. Determinant is a number, a scalar. Now this I can rearrange this. Determinants of P, P minus 1. You see, I just bring this and put together. You see, determinant of P minus 1 is determinant of I. Okay, I is equal, let's make a 2 by 2 matrix, a 1, 0, 0, 1. So determinant of I is equal, 1 times 1 is 1. See, this times this minus this. So this is equal 1. So determinant of A is equal determinant of B. Okay? This is equal determinant of B. That's a second property. Before we develop or show the third property, I would like to play a little bit with the homogeneous system homogeneous system of linear equations. Okay? Please, I will insist again, don't forget to study the 10 videos about Jordan form. You see, all I will do here will be detailed there. See, a lot of interesting topics I put in this 10 videos. You see, 10 videos. Now, what is homogeneous system? You see, I will start with a very, very simple one. Look, x plus y is equal 0, x minus y is equal 0. So, homogeneous system of linear equation, you see, homogeneous, this means that the right-hand side is 0. That's what means homogeneous. Suppose I have one over here. This is not homogeneous system. Homogeneous system, the left-hand side, the right-hand side has to be 0. Okay? So these are the unknowns. Okay, x, y are the unknowns. And the coefficient of x is 1, coefficient of y is 1, coefficient of x is 1, coefficient of y is minus 1. So, without solving, let's see. We add two numbers. For instance, 7 plus 3, okay, so let's put 7 plus 3 is 10. 6 plus 4 is 10. But 6 minus 6 is 0. So 6 and minus 6, okay. Now, satisfy this equation here. But 6 and minus 6 does not here. Because 6 minus 6 is 0. 6 minus 6, this is 12. So the only solution here, is x is equal y is equal 0. That's the only solution. Now, because 0 plus 0 is 0, 0 minus 0 is 0. You see, two numbers, the difference is 0. The same number, the sum is 0, is impossible. So, this solution here is called trivial solution, or unique solution. So, homogeneous equation, there is a test that will show us if we have a trivial solution. You see, let's work with the determinant of the coefficient. See this 1, now 1 and minus 1. So let's calculate. 1 times minus 1, 1 times minus 1, minus 1 times 1. So this is equal minus 1 is minus 2. Now, if the determinant of the coefficients of the unknowns, if the determinant is different from 0, we have a unique solution called trivial solution. If you hear trivial solution, homogeneous equation, see, all the unknowns, they are 0. Okay. Now, let's see another case of homogeneous system. Let's put here, for instance, okay, right here. No, right here. Let's change here. Now, let's see. X plus y is equal 0, and 2x plus 2y is equal 0. See, look. X plus y is equal 0, so 8, let's put x is equal 8, y is equal minus 8. You see, 8 plus minus 8 is 0. That's here, let's substitute here. 2 times 8 is 16. 2 times minus 8 is minus 16. Also, this solution also satisfies both equations. Let's put x is equal minus 1, y is equal 1. Let's put this solution here. Look, minus 1 plus 1 is 0. Here, 2 minus 1 minus 2 plus 2 is also 0. What you are seeing here, you see, that this homogeneous system, it has infinitely many solutions. You see here, see, I can, it's not, attention now, it's not any solution. When you put infinitely many solutions, for instance, x is equal 100, y is equal 200. You see, 100 plus 200 is 300, not 0. So you have to see and understand that you have many solutions, but they are not any solution that I want. Now, so there is, you see, also a trivial solution exists here, because 0 plus 0 is 0, 2 times 0 plus 2 times 0 is 0. So infinite many solution, including trivial solution. Okay, because 0 plus 0 is 0, 2 times 0 plus 2 times 0 is 0. Now, there is a test here. Let's calculate the determinant of the coefficient. Let's see, look, 1 times 2 minus 1 times 2 is 0. Now, a homogeneous system, when the determinant of the coefficient is 0 in this case, this implies infinitely many solutions. That's the test. Now, knowing this, we are going to show in the next step a very, very important concept which will be used in elasticity, strength of material, continuum mechanics, fluid mechanics, thermal science, and math in general. What I will develop here does not have nothing to do with similar matrix. No. We'll show what you call is this. Given a matrix A, find the eigenvalues and the eigenvectors. First of all, before finding eigenvalue and eigenvector, let's understand what we mean by eigenvalue and eigenvector. What do we mean by this? What does we mean? Now, you know, because we already did, you have a vector x over here. Let's put x. And I have an operator A, that is C. A applied to x, I deform, there's a deformation on x, and this is the image. So AX, this A, okay? AX, the operator on X, is equal C. So the operator X acts on vector X and result or yield the vector C. That's what a matrix does. Or if you use a second order tensor, you see dot X is equal vector C. Here we are working with the elements of A. This is the element or the components of X and the component of C. This is X1 and X2. That's what, let's put X over here. That's what an operator A does. Now, suppose I have, let's see in 2 by 2, okay? This is X1 and this is X2. The famous Xy, okay? Let's work with X1 and X2. Now, here my vector X. My vector X. Let's work with the component. Now, I want to know which X here is unknown, such that AX will, let's put AX, I'm sorry, let's draw AX here. Look. Now, which X, now X don't know, which vector X such that AX is equal a scalar times X. See? Now here X is unknown. Now A is given, A is known. A is known and X is unknown. This scalar is unknown. Okay? Now I only know X, matrix X. Now the question is, which X such that AX, this AX, is equal a scalar times X. You see, what is X such that the operator A on X just give a magnitude of X which will be greater than X if lambda is greater than 1, or less than X if lambda is less than 1, or if lambda is negative. So I'll have here this here for lambda negative. Okay? Now I want to know what is the X such that AX is equal to lambda X. Okay. Here is different. Here I know A, I know X, and I don't know C, so I calculate. You see? But here I know the only object which I know is the matrix A. Okay. Look, given matrix A, find the eigenvalues, that's lambda, and the eigenvector, so X. You see? Such that AX is equal to lambda X. Before we do any calculation, you have to understand what we mean by eigenvector and eigenvalue. See? X is unknown, lambda is unknown. See? Now I want to know which X such that A is given, operate on this vector here, or I just stress or compressed the value of x. Or lambda, if lambda is negative, okay, ax, this is a straight line, okay? You see, if lambda is positive, now ax, lambda x, has the same direction of x. If lambda is negative, I have x here, here's lambda x. So I have opposite direction. Did you understand clearly what you mean by eigenvector and eigenvalue? Now, let's calculate. Let's solve using very simple example of A is 2 by 2 matrix. Now, give me A, this I know. What I want lambda, and I want x. Let's call here x1, x2. Because it's 2 by 2, this is x. Now, let's apply the definition of eigenvector. What is the eigenvector? Ax, unknown, is equal lambda x, unknown, unknown. See? Now, from here, I can do as follows. Ax minus lambda x, you see, is equal 0. 0, 0 vector. This is 0 and 0. Okay, and purposely, I put this wrongly, just for you to see. Look, I just brought the right-hand side to the left-hand side. Now, I'll do, see, A minus lambda x. You see, there is something strange here. You see? Look, A is a 2 by 2 matrix. Lambda is a scalar. See, this is scalar. So this has to match for subtracting. That's why I have to put I over here, Ix, and this will be okay. Now, here I have A, 2 by 2, minus lambda I is 2 by 2. You see, let's write lambda I over here. Look, lambda I is equal lambda. What is I? Identity matrix. Look. This is equal lambda 0, 0 lambda. You see, this is lambda I. You see, because A is 2 by 2, minus I must have here a 2 by 2 matrix. So this will be 0, 0. See, now, you see, A minus lambda I, this is 2 by 2 matrix. X is 2 by 1. So 2 by 2, 2 here must match with this. So the result is 2 by 1. So that's why you have 0 over there. Now we use what you call the homogeneous. You see, this here, lambda is unknown. Lambda is unknown. X is unknown. So this matrix here is not A. A minus lambda I, x, this will have a homogeneous system of linear equation. Let's see here, let's see, okay. Look, now the I minus lambda I. You see, look, I minus lambda I. Okay, A minus lambda I, see. Now, let's write down here what is A minus lambda I. See, A minus lambda I. You see, so this will be 2 minus lambda. So this minus 1 minus 0. So this is minus 1. Let's put over here. Now, 0, okay, 0 minus lambda I. 0 minus 0, so this is 0. And 1 minus lambda I. So this is 1 minus lambda. See, this A minus lambda I. Now I have to solve this equation over here. I have to solve this homogeneous equation, so let's do it. You see? Look. The homogeneous equation, now A, let's put here, A minus lambda I, this 2 minus lambda minus 1, 0, 1 minus lambda, x, x1, x2 is equal 0. Okay, look, this is homogeneous equation. x1, x2 is the unknowns. Now I want non-trivial solutions. Because it's obvious. Look, for x1 is equal 0 and x2 is equal 0, obviously this matrix applied to 0, 0 will give 0, 0. So what I want this. I want infinitely solution. That's what I want. I want to find the eigenvector x. Obviously, I repeat, non-trivial solution. What I will do, what will be the procedure to guarantee infinite solution in homogeneous equation? What are? Determinant of the coefficient 2 minus lambda minus 1, 0, 1 minus lambda must be 0. See, as we showed before. So this determinant of the coefficient, you see. Now let's solve this determinant. For this, given the look, attention now, the matrix A is given. From the matrix A, I will obtain eigenvalues and eigenvector. If I change the matrix A, I will obtain other eigenvalues, other eigenvectors. See? Now, let's solve this determinant here. I'll solve the determinant, okay? Now, let's write down here. What is the determinant of 2 minus lambda minus 1, 0, 1 minus lambda? So let's multiply 2 minus lambda, that multiply 1 minus lambda, minus, you see, minus 1 times 0. So this times this minus this. So this is equal, look, I'm imposing, this is a number. Attention, determinant is a scalar, is a number. Don't confuse with matrix. Matrix is an operator. It's not a number, it's operator. Now, you see that's determinant, so this here will be 0. So 2 minus lambda, that multiply 1 minus lambda is equal to 0. So this is a second degree equation. Okay? But now it's easy because, you see, look, I put lambda 1, the roots, lambda 1 is equal 1, and lambda 2 is equal 2. See? Because for lambda is equal 2, this is 0. This will be minus 1. 0 times minus 1 is 0. For lambda is equal 1, so this is 2 minus 1 is 1, 1 minus 1 is 0, so these are the roots of determinant A minus lambda I is equal 0. Now the roots. Obviously, if I have a 3 by 3, I'll have 3 values for lambda. If I have n by n, I'll have n values for lambda, lambda 1, lambda 2. Sometimes lambda are not distinct. That's okay. Now, Did you understand now? Now, the next step, okay, look, this is calculated. Now we need the eigenvectors. Don't forget what we mean by eigenvector, okay? AX must extend or compress or change direction of the vector x. Eigenvector for lambda 1 is equal to 1. Look, don't forget, what is the equation we are solving? What equation we are solving? We are solving this equation over here. So look, this, you see, is 2 minus lambda minus 1, 0, and here is 1 minus lambda. Now, I'll call here P1 and P2. This is my unknown. This is equal 0, 0. See, look, this here is A minus lambda I is A minus lambda is 1, 1 I. You see? Look, this A minus 1 I. See? This, you see? 2 minus 1 I. So lambda, now, lambda is equal to 1. You see? Look, okay, I'll not do this. Okay, I'm not in a hurry. Lambda is 1, okay? 2 minus 1 is 1. Here is minus 1. Here is 0. Here is 1 minus 2. So this is minus 1. You see? This is apply to P1, P2 is equal 0, 0. See? Because for lambda is equal to 1. It is 2 minus 1 is 1. I repeat here because there is no minus lambda here. So minus 1. Here is 0. This 1 minus, I'm sorry, this is 0 here. Okay? Look, because lambda is 1. 1 minus 1 is 0. So you have this equation here. Let's solve for P1 and P2. Look, before solving, how many solutions do we have? How many? Infinitely solution. Oh, a trivial solution satisfies. Sure, satisfies. Look, 0, 0 satisfies. Okay, you put 0 here and 0 here. See, first row, first column will be 0. This will be 0, 0. But what I want is this. It's infinite solution. That's why I imposed the determinant to be 0, because homogeneous equation has, the system has infinite solution if the determinant of the coefficient is 0. Now let's develop here. See, look, let's put this first row, first column. P1 minus P2 is equal 0. You see, this is first row, first column. The second equation, 0 P1 plus 0 P2 is equal 0. Now, this is a system. P1 and P2 must satisfy both equations. For instance, this equation here, if P1 is 1000 and P2 is equal minus 500, satisfies because 0 times 1000 plus 0 times 500 is 0. But it has to satisfy the first equation. And the first equation, P1 is equal P2. Must be. Now, if P1 is 100, P2 will be 100. If P1 is equal minus 10, P2 is equal minus 10. You see, if, for instance, P1 is equal minus 10, P2 minus 10. Look, 0 times minus 10 is 0, plus 0 times minus 10 is equal to 0. Satisfy both. So I obtained infinite solution for this eigenvector. That's right. That's right. Let's put here, I will erase here and put my first solution. So here x is equal, I call x1, x2. For x1, let's put here, this for x1, I just called p1 and p2. This is equal, let's choose 1, 1. See? Well, p1 is equal to p2. I could put here 0, 0, but 0, 0 is a trivial solution. I want infinite solution. I could write minus 1, minus 1. So for the eigenvector is equal to, lambda 2 is equal to. Lambda is equal to over here, so this will be 2 minus 2, 0, minus 1, 0. Now 1 minus 2 is minus 1. You see, this is a minus 2i. See? Now I want to solve this times x is equal to this times x. Let's call here q1 and q2. This is equal 0. See? Now, first row, first column, so minus q1 is equal to 0. See? No, I'm sorry, minus q2 is equal to 0. See? This times this, 0 times q1 minus q2 is equal to 0. This one will be 0 times q1. I'll put over here. So look, 0, 0 times q1 minus q2 is equal to 0. Again, 0, q1 minus q2 is equal to 0. Look, q1 can be any value. For instance, q1 is equal to 1,000. 0 times 1,000 minus q2 is equal to 0, so this implies that q2 has to be 0. q1, no, because you see the same equation here, q2 will be 0. See, q1 is equal to 1,000. 0 q1 is 0. Minus q2 is 0, that's 0. 0 times 1,000 minus q2 is 0. q2 is 0. So, in this case, q1, any real value, and q2 is equal to 0. So, my eigenvector x2 is equal, no, q2 is 0, has to be 0. And q1 can be any real value, so let's put 1. So, I obtained the two eigenvectors, 1, 0 for lambda is equal to 2, and 1, 1 for lambda is equal to 1. Let's interpret what we obtain right here. Okay? Here is a summary of the example. Given matrix A, so lambda 1 is equal to 1, lambda 2 is equal to 2, are the eigenvalues, or is called also characteristic value of matrix A. Now, on the other hand, x1, x2 is called eigenvectors. Let's put the eigenvectors or characteristic vector. Characteristic let's put the characteristic vectors. Now let's draw what's written here. So look, A x1 is equal 1 x1, or k, you see, x1 is 1, 1, or k times 1, 1. 2, 2, 3, 3, minus 10, so k now belongs to the real R. The same here, so this x2, the second eigenvector, 1, 0, or k times 1, 0. For instance, minus 3, 0, 10, 0, 100, 0, you see? Now, in A, x2 is equal to x2. Now let's draw. You see? Let's draw here. Okay. Now this is my axis, x1, and this is my axis. Let's put small letter here. x1 and x2. Now, the vector capital X1 is 1, 1. So this 1 and 1. So this is the eigenvector. Now let's do, for instance, ax1 will be, for instance, put k is equal to 2. Then it will be here 2 and 2. See? This is an eigenvector 2. See? Now put k is equal minus 1. You see? Look. This will be minus 1 here. So this will be this vector over here. So all of vectors that lie in this straight line, okay, is the eigenvector or characteristic vector of matrix A, of matrix A. Don't forget that. And these are the eigenvalues. Now let's draw the second eigenvalue, 1, 0. So this is 1, 0. You see? 1, 0. Now for k is equal to, you see, this here is also is to 0. So k is equal minus 1, so this is 0. For k is equal minus 2, so this vector here is the eigenvector corresponded to lambda is equal 2. You see, now, in this case, okay, x2 is equal 1 or multiple of 1, 0. You see, so this here, that's important. x1 and x2 can be a basis for the space R2. You see? Because x1 and x2 are linearly independent. So this is x1, this is x2. So the form can be a basis for R2. They span the space R2. Now let's see the third property of similar matrix. We solved and got x1 and x2, lambda 1 and lambda 2. Now, ax1 is equal lambda 1 vector x1, ax2 is equal lambda 2 x2. Let's put all together. Now, A here is x1, x2 is equal. Now, here is lambda 1, x1, lambda 2, x2. So, now here is this is the first row, the second column. See that? Look, ax1 is equal lambda 1 x1. Ax2 is lambda 2x2. But recall that A, you see, this x1 in this case will be 1, 1, and x2 is 1, 0. You see? This is x1 and this is x2. So this is equal lambda 1. Let's put lambda 1 is 1, but let's do this. Lambda 1, now I'll put this here. Now here is 1, 1. You see? Lambda 1, 1, 1. And here, lambda 2, 1, 0. You see? That's just for you to see here. Now, you see, A times this matrix. Now, this you can write like this. Look, I'll put here 1, 1, 1, 0, and here lambda 1, lambda 2, 0, 0. You see? Look. We'll multiply the first row times this first column. So this will be, I put here what's equal, okay? I put over here. Here, look. Lambda 1, this will be lambda 1 over here. See? Now, second row, first column. So this will be lambda 1 over here. Now, first row, second column. So this will be 0. You see, this one times this, plus this is lambda 2. Let's write down here lambda 2. You see? Now, second row, second column. So this will be 0. You see? Now, from this, we can see clearly that we can put, let's call this P, this will be P. You see? Now, this I call big lambda, called diagonal matrix. So, AP is equal P capital lambda. So you see, AP is equal P capital lambda. From here, capital lambda, I'll just write down for minus P minus 1, P minus 1. So this is I. So capital lambda is equal to P minus 1, AP. What is P? P is a transition matrix, and here are the eigenvectors. You see? In the column here is the eigenvector x1, and here the column vector 1, 0. So A and P, I'm sorry, A and capital lambda are similar matrix. See? Now, the first property we saw that trace, okay, let's put here A similar to B. B is not necessarily the diagonal matrix, this in general. Now, here we can write the A is equal P, B, P minus 1, or B is equal P minus 1, AP. See? Because they are similar. Now, the trace of A is equal trace of B. B is similar. The second property, determinant of A is equal determinant of B. Now let's see the third one. Look, AX, let's put, is equal lambda x. Now, do you remember when we put over here E1, E2 is equal, now P, this is prime 1, E prime 2. Remember? So this is x1, x2, and we rotate x1, x2. This will be the x1 prime and x2 prime. We made the exercise rotating 90 degrees, and I left for you to do for theta is equal minus 90 degrees and 180 degrees. I hope you did that. Now, let's do this. So, this is x1. So, I can write down, if I want, a vector x is equal py. Y is related to x1 prime, x2 prime. So, here I can write like this. So, x, let's put py over here. So, a, p, y, because x is py, this is equal lambda x is py. So, assume that lambda is an eigenvalue of matrix A. See? Now, attention now what I will do. Now here, see? I multiply by p minus 1. So, p minus 1, A, p, y is equal lambda p minus 1, py. You see? I just multiply both sides by p minus 1. You see? P minus 1. Lambda is constant. Now, what is p minus 1 times p? This is I. So this is equal lambda y. You see? Lambda y. And also, what is this? This is b. You see? Look at that. B is p minus 1 AP. So, by is equal lambda y. Now, you see? by is equal lambda y. So lambda is also an eigenvalue of b. You see? So, lambda is an eigenvalue of A, and lambda is an eigenvalue of B. So, the third property, if A and B are similar matrices, so they have the same eigenvalue. So, for this a general case, you see, this is, I put general case. Suppose the case we just did previously. What we did, you see, that's the third property. I will apply this third property. We know that AP is equal P capital lambda. Now, this P here are construct, okay, based on the eigenvectors. You see, this is not any P, okay? Do you remember the columns of P are the columns of the eigenvectors? So, you see, look, do you remember? Look, this is A, let's see the x1, x2. This is P, okay? Look, A, what is x1? Remember, 1, 1. x2 is 1, 0. This is P. This is eigenvector. So, if P is eigenvectors, AP is P capital lambda. So we conclude here that the eigenvalues, look, the eigenvalues of, I would like to write down here, okay. Look, we conclude that the eigenvalues of A are the same of the lambda. You see? I have a matrix A. You see, in videos and books, they say the word diagonalize a matrix A. See? I don't like that term. See? Because you see, they say, okay, give a matrix A, diagonalize the matrix. I prefer, okay, you see, it takes a little bit longer, the text, but I prefer this. Find a diagonal matrix in which is similar to A. Because I don't know, see, diagonalize a matrix, for me, it seems that, for instance, I had 2, the one I did, -1, 0, and 1. Diagonalize the matrix A means that I raise here and erase here. So I would prefer that I respect, okay, books and videos and professors that use it to say diagonalize the matrix A. Particularly, I don't like, you see, because I repeat, I would prefer this. Give a matrix A, try to find a diagonal matrix in which is similar to A. You say that, I know that this takes a little bit longer, okay, but for my viewpoint, that's correct, and you understand, see?